Tonight, for our main presentation, Diane Hall is the speaker. I almost feel like I don't know how to introduce her because everybody, anything I say, everybody already knows, right?
We got new people.
I mean, she's obviously our current president, just elected to that office for this year, but she was our president before and has held, I don't know how many other offices. I've served on the board with her for years. Really glad that she's willing to run for president again. From our most recent president here. And one of her favorite things is observing globular clusters. That's what she's here to talk to us about tonight.
All right. So yeah, as Dale said, globular clusters are one of my favorite things. And it wasn't always this way. When I was a young person, and I do mean a child, reading about astronomy and having it capture my imagination, globular clusters were not high on the list. Other galaxies? Oh yeah. Exoplanets, which never even been verified yet, sure. Open clusters? Totally. But after we invested in some real astronomical equipment and started truly observing, Jonathan and I fell in love with globular clusters. And hopefully by the end of this presentation, you might be a little more excited about them than you were when we convened the meeting tonight. So, what's a globular cluster? There are many star clusters that have worked their way into human culture. Here is a famous reference to an open cluster, that being a reference to the Pleiades or Pleiades, the dazzling, visible to the naked eye cluster in Taurus, that made its way into the book of Job, one of the oldest parts of what we call the Bible. There's the Pleiades there on the left-hand side. You can see its dazzling blue stars with the wisps of trailing nebula. Then we also have the Hyades, which were another cluster known to the ancients, associated with weather and seasons. Almost there, Marty?
Got it. There you got it.
Yep, cool. And I believe there's a reference in Homer. And you've got Praesepe, aka the beehive, aka the gate of men, known to Ptolemy, one of the first things seen by Galileo when he first started telescopic astronomy. These are beautiful. These are great. We're not talking about those tonight. So the globular cluster, and this one here is M3, located in the small but interesting constellation Canes Venatici, the hunting dogs, are a different beast entirely from the groupings of very young, very hot stars that make up open clusters. You might even be able to see a color difference between this and, say, the Pleiades that we'll go into shortly. So open clusters are straightforward. They are new stars born out of the same cloud of gas and dust that have not yet drifted apart. We see them in configurations because they are close. Not so with globular clusters. For a start, they're not new stars. They contain, or at least some of them contain, some of the oldest stars, not just in our galaxy, but in the universe. And that was the simple version of the story that, say, I gave to people at outreach events for quite a few years. They're old stars, they're packed into tight round clusters, and they orbit galaxies like the Milky Way in a halo. This is a distribution showing you've got our disk of the Milky Way, and you've got all these globular clusters scattered around. Well, hold that thought, because why would all these things be orbiting a galaxy in a halo? We'll get to that. Well, one reason that the stars look distinctly different from the stars in an open cluster like the Pleiades is they're metal, meaning they're hydrogen fusing into helium. They don't have the heavier elements that you find when stars are made out of recycled material. So our star, the sun, has trace elements of quite a few different things in there, and thankfully our solar system formed out of a cloud that had metals like iron, minerals like calcium. We wouldn't be able to exist without those elements. Metal-poor stars, no. They are known as population 2 stars in scientific nomenclature, and they were formed close to the beginning of our universe, back when really there was hydrogen and a little bit of helium and maybe a little bit of lithium. They've been around for a while. Since these are old, fairly cool stars, otherwise they wouldn't have lasted 13 billion years, they tend to have a red or maybe a golden cast, unlike the blue and white you see in most open clusters. So this is M80, and you can just see it's yellow with bits of red. These stars have been through a lot. So, we've got these balls of ancient stars that just happen to circle galaxies like the Milky Way in a halo. Here's another image of these old population 2 stars that just so happen to be in our galactic center and in all these globular clusters. Why would you have that distribution? Well, the ancient origin of globular clusters has been re-examined lately. And it turns out, oops, my picture didn't save. Not all globular clusters are filled purely with ancient stars. Some of them appear to be the cores of other galaxies that have been captured by larger, more massive galaxies like the Milky Way, like our sister galaxy Andromeda, like the massive M87. And what we see as globular clusters are galactic cores of other galaxies that went through a couple of populations of stellar evolution, got captured, got stripped of all their star-forming dust, and now exist as just balls of naked stars with maybe a black hole in the center. So young globular clusters with ages up to 1 billion years, which is still a long time, but quite different from 13, are indicated in this image from the University of Hong Kong by blue dots. And these dots are linked together by a filamentary network of cool gas, which shows up as the orange and the white. So this is at the Perseus galaxy cluster. This is a network near the center of it. So the more work we do on globular clusters with the tools that we have available to us now in this century, the more we're realizing it's not as simple as these primordial balls of stars just so happen to neatly encircle a big galaxy. There's also dark globular clusters. So these were hypothetical, just there's globular clusters that might have an unusually high mass for the number of stars, populated by objects rich in dark matter, and probably central black holes that were quite massive compared to the diameter of the cluster. These were proposed back in 2015. Well, come to find out, the ESO, European Space Organization, their very large telescope in Chile, found evidence for these dark globs around the galaxy Centaurus A, which is shown here. So you've got dark globulars circled in red, you've got normal ones circled in blue, which quite outnumber the dark ones, and you've got a scattering of red globs that show similar properties to dwarf galaxies, which again might have been captured and stripped by Centaurus A. So you've got one kind of object that at least here has 3 different populations. So it's a lot more complicated than the story I used to give to people when I was showing them my favorite globs in a telescope. Now, rather than just yammer on about general properties of globs, I hope that a little walk through my favorites might help demonstrate what we learn from them, how we learn from them, and how cool they are. So we're going to start with the very first globular cluster to be discovered as such. Not the first one humans ever saw or put on a star map, but the first one that was identified as a thing that was not like anything previously seen and cataloged. We call it M22. It's located just south of the ecliptic, the line going across the plane of our solar system, just to the left of the top of this dome of the Sagittarius teapot. Now there's a whole lot of stuff there. M70, M55, M8, M21. M22 stands out. It's big and it's bright. It was discovered on August 26th of 1665 by a German amateur astronomer named Abraham Ile. Unfortunately, he's obscure enough I couldn't find a photo of the man, but it was included in Charles Messier's catalog of comet-like objects in 1764. So it was around, knowledge of it existed for 100 years before Messier began cataloging things that are not comets that annoy me when I am looking for comets. However, it didn't really get serious study until 1930, when the guy on the left, famed American astronomer Harlow Shapley, found it had 70,000 stars and a dense core. This was right at the same time that everybody was retooling their view of the universe itself, realizing that we were not simply one huge galaxy that encompassed everything in the universe, but we were one of many island galaxies out there in space. And in the middle of that big shift in how astronomers viewed our planet and its place in the universe, Shapley was also digging into, okay, what are these things? What are these balls? What are they? What is this? After World War II, this line of research was picked up by a guy called Halton Arp, aka Chip Arp. Some of you may have heard of him because he liked to compile weird galaxies. And he also has some very unconventional ideas about, yeah, we're not going to go there. So anyway, he dug into this particular weird object, M22. Well, it has what's called a red giant branch sequence of how its stars are distributed. And people noticed in the latter half of the 20th century that this sequence of this star distribution was awfully like that of another object called Omega Centauri that we'll be discussing in the latter half of this talk. Well, by 1977, that made M22 very interesting to people. And more research was done on it. We now know it's one of 4 globular clusters to have a planetary nebula. So one of its stars has died and puffed out a glowing shell of gas and dust that we can detect from Earth. It contains 2 known black holes. So not just a central black hole, but at least 2 of them. It's also so big and bright to us because it's one of the nearer globular clusters to us. It's 10,600 light years away, which is far, not nearly as far as some of the things we're going to be talking about. And it has a convenient position in the sky near to our actual galactic bulge, so it and its density can be used to micro-lens objects behind it so that astronomers can see other things that would be otherwise hidden at the core of our Milky Way. So, it's a cool object. It's also very pretty. This is one of my favorite quotes about any globular cluster by Robert Burnham, who did the 3-volume Burnham's Celestial Objects, which is an invaluable mid-20th century guide to stuff in the sky. It has always seemed to the author, Burnham, that J.R.R. Tolkien in his delightful fantasy, The Hobbit, unwittingly created a description of M22 when he spoke of the fabulous jewel called the Arkenstone. Hobbit is not one of my favorite books. I like it, I don't love it, but I love this piece because it's beautiful. And what did Tolkien say of the Arkenstone? A globe filled with moonlight and hung in a net woven of the glint of frosty stars. Yeah, that's a nice piece of celestial jewelry. I will admit that under very high magnification, and I'm viewing it from a mountaintop with a 3-foot wide telescope, it's a bit oblong, it's a little messy or smeary. It looks best viewed from a respectful distance. My 15 by 70 binoculars, it's beautiful. My 10-inch reflector, beautiful. 3-foot wide reflector, okay, there's some other things that look better. Observing it is relatively simple if you can get a decent southern horizon in the summer. Good luck with that in Metro Detroit. You might want to go to Canada. It's often underrated by northern observers because it's so low and so often lost in the glare of the horizon. So that was the first blob. Now I'd like to talk about M4, which is a slightly weird one. It's located in Scorpius, not far from the bright red star Antares. It was discovered in 1746 by a French astronomer, Philippe Loy de Chezeaux. And unlike many globular clusters, it doesn't have a dense bright core. It's not a ball of jewels so much as it is a ghost. Definitely one of the objects that you could think, oh yeah, I could see how somebody could mistake that for a comet, especially using an 18th century telescope. But I do love searching for it in dark skies with my 15 by 70 binoculars, and especially when I can fit it in the same field of view as Antares, because that brilliant red star and this ghostly glow, they look real nice together. Scientifically, M4 had its own contributions to make. So its odd nature made it the very first glob to be resolved into a ball of stars. Charles Messier, who didn't necessarily see the stars in many of the other objects he cataloged, pale glow, no stars resolved, etc. He knew that this was a ball of stars when he added it to his list of false comets that we know as the Messier catalog in the 1760s. So I think that M4 deserves its own little bit of credit for alerting people, okay, there are these things, they are round, they are glowy, they are pretty, there's something different about them compared with everything else that we know. Then we've got M13. Who there in the audience has seen M13?
That's not.
Yeah, exactly. Who is not? Okay. This one is positioned high in the northern sky in the constellation Hercules, beautifully placed for the spring and the summer for our latitude. As such, it is a big hit at our summer star parties. I think poor Jeff McLeod had to focus on it for about an hour at astronomy at the beach one year. 3 hours?
Yeah, 3 or 4.
3 or 4 hours. Okay, it's famous. It's the Great Northern Globular Cluster. It's mostly, in my opinion, that famous because it's easy to spot, especially from where we are. I think there's a lot of prettier globs in the sky, but I will say it's got some fascinating details. If you look at this, not so much at this resolution, but from this exact photograph taken by the Hubble telescope, you can see traces of an interesting 3-part structure. So it has 3 intersecting dark lanes known as the propeller, because it looks like an old-fashioned 3-bladed propeller. This can be seen by amateurs in a 10-inch telescope. It's actually not hard if you know it's there. I've also seen it in much larger telescopes, but dark skies and a 10-inch dot, you will see it. So it's located in the constellation Hercules. If you've never seen this object, get your scopes ready this spring. If you have seen this object, but the propeller has escaped you, either break out your biggest scope or borrow one or come to one of our events and say, hey, I want to see the propeller in M13. because it is really cool. Now, this is one of my absolute favorites. M5 adorns the little loved constellation Serpens Caput, head of the serpent. It's in an area of the sky that doesn't have that many bright stars. And that makes it difficult to jump to it the way that you can say, okay, to find M22, find the dome of Sagittarius, go to the left. To find M13, find the keystone of Hercules, and it's along one of the sides. Easy. If you have a dark enough sky, you might even be able to see these things without any magnification. M5 is just off on its own, kind of floating in some mediocre constellations above the ecliptic. You may need go-to to find it, you may need push-to to find it. If you're like me and you don't have that, you may need to consult your star charts repeatedly. It is totally worth the effort. This was discovered by the German astronomer Gottfried Kirch in 1702, and it was first resolved into stars by William Herschel in 1791. So for those of you not super familiar with Herschel, he was the greatest visual astronomer of his age, maybe any era, and he had the best telescope around at the time. Herschel alone unlocked many of these fuzzy patches of light that Messier and other contemporary astronomers could not see the stars in, and said, I see the stars, they're stars, they're star clusters. And Herschel unlocked this one. I viewed M5 several years ago under near ideal circumstances. It was 7,000 feet elevation in a national forest through a 36-inch telescope in Arizona. High, dry, clear, dark, big telescope. M5 skyrocketed to the top of my favorite Messier objects because it went from just being, it's a pretty good globular cluster that's kind of hard to find, to this thing is gorgeous. It has amazing symmetry. It looked like a lotus blossom. It just so crisp, so clear, so orderly. I had to admit that my beloved M22 was kind of a mess compared with M5. But then I had a new favorite object, so, you know, everybody won. Now we're going to talk about something that looks really lousy. So M54 was a real disappointment to me the first time I saw it. Jonathan and I were up in our favorite dark sky site on the Lake Huron coastline, and we were burning through as many Messier objects in the vicinity of Sagittarius and Scorpio as we could in one summer night. And we looked at M54, and it says, okay, it's just a mediocre fuzzy thing in Sagittarius, which is filled with mediocre fuzzy things. It doesn't offer immediate gratification the way that M22 and M13 do. Even large amateur telescopes can't resolve this one into stars. Then Jonathan pointed out to me why this was so faint and so ridiculously fuzzy. It's outside the Milky Way. It's interstellar. It orbits the Sagittarius dwarf galaxy. For something interstellar, that's pretty cool. You won't get the chance to see it like this. This is another Hubble image. And it's partly in infrared. But it's a pretty thought-provoking thing when you go and you look at it and say, yeah, okay, it's mediocre, but it's mediocre coming at us from a long, long, long distance. So when Messier discovered this one back in 1778, he wouldn't have had no idea that the cluster belonged to another galaxy because they didn't have a standard belief of there being other galaxies. We're in a universe outside Messier's wildest fantasies, and that makes M54 pretty cool. Now, the moment some of you have been waiting for. The king of globs, Omega Centauri. So the name should be a giveaway that this is something special. It has a star name, a Greek letter, followed by the name of the constellation. This was bright enough to be logged as a star in 150 AD by the Greco-Roman writer and astronomer Ptolemy. He cataloged it in Almagest as a star on the back of the centaur. Let's flash ahead to 1603. Johann Bayer in Germany is using Ptolemy's data to make a newer, better sky chart called Uranometria. And he designates it by the new system of the Greek letter followed by the name of the constellation and calls it Omega Centauri. Well, it's hard to see from Europe. European astronomers apparently didn't give it a lot of thought for a while. So we flash ahead to 1677. English wonder boy, Edmund Halley, is off on the island of St. Helena in the Atlantic, middle of nowhere. With the aid of his telescope at that latitude, Halley recognized it as a non-stellar object, and he reported it to the Royal Society as interesting things. He made his own catalog of them and submitted it, and there it stood. It wasn't until 1826 that the Scottish astronomer James Dunlop recognized that this star, aka fuzzy thing, was in truth a beautiful globe of stars. So I was fortunate enough to see Omset last month from a dark sky site on Maui. I have to say that in my favorite pair of 15 by 70 binoculars, which with I have appreciated M4, M22, etc., it stuns. It just pops out of the eyepiece as a snowball. It's really worth the trip. If you have the opportunity to go, I would say south of 25 degrees latitude, find a way to bring some optics and see it. I've seen it from outside Las Vegas. I've seen it from Hawaii. I've seen it from Arizona. It's just, it never fails to stun me. It is a truly amazing object. And it's a challenge object because, believe it or not, it can be seen from European countries or from Canadian soil. I've talked about this before, but this is the time of year to start planning it. Hook up with the Royal Astronomical Society of Canada, Windsor, right across the river. From their dark sky site in Point Pelee National Park, you can see Omega Centauri from the 42nd parallel on Canadian soil. And that 2 or 3 day window of time where you can do that is coming up. This picture was taken, it doesn't look like much, but it was taken from Italy. If you live far enough north, it can be a fun challenge. I will now sing the praises of something I haven't seen. It's on my wish list. 47 Tucano. I have never ventured south of 20 degrees north latitude. I've not seen the constellation of Tucana. This one is 18 degrees from the south celestial pole. Obviously, that far south, Ptolemy was not aware of it. The early European astronomers were not aware of it. I don't think the Chinese astronomers were aware of it. It wasn't until the 1750s when a guy called Nicolas Louis de Lacaille was observing down from South Africa. And he realized this was a cool cluster. Previously, it had been mistaken and briefly cataloged as a star, Xi Tucanae. But now we know it's not. It is a dazzling, amazing globular cluster that is said, again, I cannot speak from personal testimony, to rival the great Omega.
No question.
Yes?
No question at all.
Oh, okay.
Spectacular.
Yeah, so we've had some people fortunate enough to have seen it with their own eyes and scopes here in the crowd. So it is the second brightest glob after Omega Centauri. It telescopically reveals about 10,000 stars, may have an intermediate mass black hole in the center, and it's been used, most intriguingly, for exoplanet research. So it's been studied repeatedly to see if it has any exoplanets. First, the core was studied, and the Hubble Space Telescope was one of the instruments involved. This was around the year 2000. Nothing. Then later, I think this past decade, they studied its outer fringes to see, well, maybe there's exoplanets lurking there. Nothing. So this contains two different populations of stars, which means that planets are not impossible, but they just don't seem to be there, and maybe most globes have no such thing. If this is a typical globular cluster, it just may be an indicator planets and globular clusters don't mix. What it does have, in addition to the two populations of stars, is hundreds of X-ray sources, 25 millisecond pulsars, and stars that do indeed appear to be 13 billion years old. It's a cool object. So I hope those pretty pictures made you a little bit excited about getting to know some globular clusters, because now I'm going to go to the weird end of the family. Real challenge objects, the faintest of faint fuzzies, more obscure than the most disappointing things on the Messier list. We're talking things that were found by the Palomar scope when they first fired up the mighty 200-inch reflector after World War II. The Palomar list. Well, the Palomar list has 15 objects. I have been fortunate enough to see 4 so far in my life, all of them from that 7,000-foot elevation observing site in Arizona in the company of Joe Tocco, former officer here, who sadly couldn't be here tonight. The list contains 2 ringers, 2 objects that were known and cataloged before Palomar fired up and saw first light. One of them was actually discovered by the American astronomer Lewis Swift, who's mostly notable for the great number of comets he discovered in the late 19th century. So he discovered Palomar 7 in 1889. It's doable. An amateur can find this one. But it wasn't that exciting, so people forgot about it. And again, 1890s, globular clusters were not at the top of researchers' interest. It was rediscovered by the Palomar Sky Survey in the 1950s. So you need a big telescope and you need dark skies. But Palomar 7 is actually legitimately pretty. I couldn't see this beautiful golden color, but I could see it with a globular cluster and a nice one at that. The rest of the things in the list, yeah, they are challenge objects. You're not seeing them because they're pretty, you're seeing them because seeing them expands the mind or captures the imagination. And to close out the list, we're going far, far out. Mile 2. It is, in terms of absolute magnitude, the brightest cluster in our local group. However, it has an apparent magnitude of 13.81, even though it has twice the mass of Omega Centauri, because it orbits the Andromeda Galaxy. We won't be stealing this one until we merge with Andromeda, so don't hold your breath on that one. Even so, and this is a 20-inch telescope, so you take the dog, our dog, to a dark sky, maybe we could see something. However, if you're the Hubble telescope, it's pretty. It's a nice club. Because of its widespread distribution of what they call metallicity, that indicates multiple star generations, so not just those metal-poor population 2 stars, but population 1 and other things that aren't so easily categorized, that appear to have been born over a long period of time. It's very likely that this is not a true globular cluster in this old sense of it's just an ancient ball of stars that's been sitting there since the beginning of the universe. It's probably the galactic core of a galaxy that was captured by Andromeda and stripped. So, nonetheless, it's pretty. If you're Hubble. If you're not Hubble, well, pictures are free. So, there's a lot more I could talk about. I could talk about M15 and Pegasus, M3 and Canes Venatici. I could talk about the beautiful pairing of M10 and N12 and Ophiuchus. I could talk about some of the other southern globs that were never going to be on Messier's list because he couldn't have seen them. And I can talk about the globular clusters around, say, M87. But I'm hoping that this gave you a taste of how cool they are and how beautiful they can be both to the eye and to the imagination. And there are literally hundreds of globular clusters worth your attention, from excellent, if underrated, Messier objects to the intergalactic fuzzballs. All I can say is I recommend get that tank of gas, go to a dark sky site, head on out with binoculars or telescope, and experience them all for yourself, because it's worth it. And that concludes my talk, because I would love to answer your questions.
There is a thought that Omega Centauri may in fact be a captured galaxy.
I find that almost certain, yeah.
Because it's like 1,000,000 stars or some ungodly number.
Yeah, Omega Centauri to me, if that's a really good candidate for this, is actually a dwarf galaxy that we siphoned off all the gas and dust from.
And like I said to you before, 47 Tucani is worth the trip.
Oh yeah, Tucani's on my wish list. Haven't got there yet though.
Omega Centauri, I lived in San Francisco. You
Talk
can see it from
loud so people back there.
there. Omega Centauri, you can see that from San Francisco, that you go to the top of Mount Tam, and there's a certain time of year, everybody goes up there for the big star party, and says, okay, well, these mountains go this way down the ocean, look right there. And you can see
That's cool. Yeah, you can see it. You can make it a challenge object for New York City.
Yeah.
Jonathan and I were super pleased to see it from just outside Las Vegas. Basically, we went up a mountain just to the west of Vegas that blocked the lights of the strip. There it was. It's cool. Yeah, if anybody's interested in trying to see it from Canada, let me know, because that's something that's been on my personal wish list for quite a few years now.
I've read somewhere that M31 Andromeda Galaxy has 2 or 3 times as many globular clusters as the Milky Way. Is that partially due to the fact that we can't see many of them in the Milky Way because of the dust clouds, or do you have any comment on that?
I was actually looking into that, and I was following the line of thought that the number and the disparity of our globs versus Andromeda's tied into the old belief that Andromeda was twice as massive as the Milky Way. I don't recall coming across a definitive answer.
There must be quite a number of Milky Way globulars that are probably obscured, aren't they, by the...
Well, they might have shown up on infrared, so it's certainly a lot of things are obscured by visible light, but it would be interesting if, when the James Webb fires up, if we detect anything in infrared with the new best telescope around that was previously missing.
Yeah, and also, our galaxy's globular clusters are not, for the most part, in the plane of the galaxy. They're in the galaxy's halo, so you can often see them looking above or below the plane of the Milky Way. So they're not necessarily obscured then.
Some of them might be, but not too many, probably.
I have another question for you.
Yes.
When they first started looking for planets, as it were, I know they targeted globulars because of the number and found that many of them were red stars, or that didn't have a lot of heavy elements, as you mentioned. But I also found out, or just getting clarified, there were several of the globulars that you said had other populations that would entertain that.
Right.
Could you elaborate a little bit on that for me?
So if we were coming from the perspective of the old belief that these are simply balls of primordial stars that have been slowly burning for 13 billion years, you wouldn't expect to find planets anyway. What would they be made of? They can't be made of iron. They can't be made of carbon. They can't be made of silicon. They can't be made of any metal. They would be basically failed stars made out of hydrogen and helium. Okay. But if you have later stars like our sun that have condensed out of a cloud with oxygen, nitrogen, silicon, aluminum, etc., then the potential for there to be a rocky planet or a more familiar ammonia, methane sort of gas giant is there. In the case of Tucani 47, which has multiple population stars, they still haven't found anything. So, you know, it could be that the stars, even in the globular cluster, the stars are not so close that planets are impossible. You know, they're not packed in as tight as you think. But if these are former galaxies that the dust and gas got stripped away from, what else got stripped away? What else got slung-shot out of the systems? And then once the gas and dust is gone, there's nothing left to
build.
make planets. So it just could be that the way that clouds are composed, they're flat out inhospitable to planets as we know them.
Thanks.
Okay, yes, Bill.
Getting back to your comment about tightly packed, I've seen a lot of globulars through the telescope. And often I imagine being in a spaceship flying through them, and often wondering how far away in light years can we assume, like M13 for example, that the center core, how far away these stars are. So if we fly a spaceship through them, obviously they're so far away we'd never hit one. Do you have any idea, like Omega Centauri or M13, the light year distance of the stars in the ball?
I played a bit around with that a little bit because that is a super interesting thought experiment, and I've always liked the idea that's been proposed by some of the more poetic astronomers, like imagine standing on a planet which doesn't exist in the middle of a globular cluster, and you know, would all the stars be like first magnitude stars blazing around you? Could not figure out the actual math on it, not my strong point, but I did remember this. So you've seen televised depictions of our movie depictions of a spaceship going through our asteroid belt, right? And you've got the Enterprise or whatever, Millennium Falcon, dodging asteroid. And in reality, it's not like that. The asteroids are so far apart, you're not going to see them. Now you take that on a stellar level. So I was like, okay, so let's imagine, take the density of the asteroid belt and then take that from the distances in the asteroid belt out to the distances of 1, 2, 3 AU. Yeah, it's, I don't think it's going to be like asteroid surfing. I do think it could plausibly be, depending on which cluster. Of course, Omega Centauri is going to be way different from M4. Like, you know, if you could be on a planet on the surface, the average magnitude of stars in your sky are going to be a lot brighter than anything we've got.
I mean, in our area of the galaxy, I mean, our nearest star, apart from the sun, is about 4 light years away. So if the typical spacing is on the order of 4 or 5 light years here, now think of something like M13, which I don't remember exactly, but I think the diameter of the ball is 40 or 50, 60 light years. So if they're spaced typically about 4 or 5 light years, that's not that many stars, several dozen, but it's hundreds of thousands of stars. So the average spacing is way closer.
Right, like M13, they predict 200, 300,000 stars in the ball.
Yeah.
But like you said, Dale, they're probably 3 or 4 light years apart.
No, they have to.
At the core, they would have to be more. On the fringes, they would be, I mean, because you can see the density change through most globular clusters.
Through much of it, they're going to be spaced on the order of a light year or a lot less.
Okay, so you think it's down to like 1 or less than 1 light year?
Less than 1 light year.
Okay, which is still a long way away.
Yeah.
The radius of M13 is 84 light years.
But also keep in mind that we are not really seeing a lot of supernova remnants. So you're not seeing stars packed into the kind of, you know, the density that is causing binary pairs spiraling into one another, or white dwarfs sucking off so much that they go thermonuclear. So it is weird how few interesting objects there seem to be in these globular clusters. You know, again, like there's 4 of them that we've seen in planetary nebula. That just seems a bit weird to me. So they're not, whatever is in that system, it's not exactly space as we know it in our neighborhood.
I vaguely remember, and don't hold me to the numbers, that in our area of space, stars, it's about 0.04 stars per cubic light year. And in a globular cluster, it's like 40 stars per cubic light year. Those numbers are just vaguely, I'm vaguely remembering those. Those could be off.
They're still a long ways away.
Yeah, yeah.
Miles wide, yeah, miles or kilometers.
Yeah, they're not close, they don't seem to be close enough that they're all spiraling into the, and they're not close enough to be colliding with one another.
Right.
Yeah, but if there were planets orbiting them, then with such a high density of stars, inevitably they're going to pass near each other on the scale of hundreds of millions of years or a billion years and disrupt planetary orbits.
And that whatever influence the host galaxy has is probably doing havoc with planetary orbits too. Yeah.
That's a good point, Dale. Yeah, it would.
Yeah, it's not about collisions. It's about passing near enough to each other for their
Slingshot.
gravity
Something
to
else.
mess up orbits.
Spun around and
And
stuff.
the actual globular clusters are actually gravitationally bound too, so
Yeah.
Yep.
there's all that going on as well.
Yeah,
And they've got to be close enough for that to matter.
right.
Both M13 and Omega Centauri are 84 light years in radius. Both of them are. And that's an interesting data right there, because how much do you stick 1 million stars, like we said?
In 84 light
into
years.
84, well.
Yeah, double that.
Double that, 160. That's pretty stunning.
Okay, are there any other questions? Let's thank our speaker again.